Now let's have a look at intersections and unions of regions. Now we've already used these words when we've been referring to sets, and we've seen that when we have a Venn diagram showing two sets, A and B, we can represent the union of the two sets by saying, hey, that's really anything that's A or B. Now you can shade the A circle and the B circle and then reason that everything you've shaded is in the union, or you can literally just start from the beginning and say, let's shade the lot. Whereas an intersection between sets A and B will be only the part that is A and B. And again, you've got two choices. You can say, well, this is A, and you could shade it lightly. And this is B, and you could shade it lightly. And then the part that you've shaded twice, you can shade darker. And that's not a bad strategy when we're doing our graphing of regions, in case we've got a tricky one. Other times we can just say, look, I can see that this is the only part here that's A and B, and we can jump straight to just shading the intersection. It's up to you. So we can use these same concepts with regions. For a union of two or more regions, anything that we've shaded for any of the regions is going to be part of that union. So if it's shaded at all, it's in the union, we can just get shading. But for an intersection of two or more regions, it has to be only the part that is shaded, well, for an intersection of two regions, it would have to be the part that you shaded twice. For an intersection of three regions, it would have to be the part that you shaded all three times. And you've got that choice. You could shade each one lightly, and then you could shade much darker anything that's been shaded every time, or you could reason where things have to be and then just hop in once and shade the region that is the intersection. Now an example, let's shade the intersection of these two regions. Now before we even shade these regions, let's shade the lines that create them. So we need to graph y equals x squared, and we need to do it with a dotted line because we don't have an equals sign there, so we can see that it's not going to be part of its region. So I can rough in here a dotted line for y equals x squared. And then perhaps this one would be easier to graph, x plus y equals 2, if we rearranged it to say it's y equals negative x plus 2, just getting the y on its own there. That helps me see that I'm going to have an intercept of 2 and a gradient of negative 1, and I'm going to need to do a solid line, so it's going to look something like this. And I can label that y equals, or we could actually label it x plus y equals 2, couldn't we? It doesn't really matter either way. And we can put some arrows on the end of that. Okay, now we've got to think about our region here and what's going on. So if we were to graph this one, we've already seen in an earlier example that we want large values of y that are taller or higher up than our parabola. So if I'm graphing just this region on its own, I'm graphing everything that's above the parabola, and I could actually go ahead and shade all of this here. Now, rather than shade it and make my drawing messy, I'm just going to imagine where I'm going to shade for each one, and then I can put it together and see which sections I would have shaded twice. So I need to shade all of this and all of this just to satisfy this. Now to shade this region here, I haven't got the x or the y on their own there, but I do in this version of it, where I've effectively just subtracted x from both sides. So here I can see that I want low y values that are lower than my line. So in other words, I want ones that are below the line here. Now, a quick inspection to just check. If I sub in 0, 0 to this one, is 0 plus 0 less than 2? Yes, it is. So obviously, if I'm wondering whether I want the upper side of the line or the lower side of the line, that's confirmed I want the lower side. So that tells me that I need to shade just this region inside here because it is both below the line and above the parabola. And there I go. Now, one thing I need to be really careful of is my actual boundary points here. So firstly, I haven't labelled them and I haven't marked them with open or closed circles to show whether they satisfy these two independent regions and whether they're actually part of my intersection. So this point here, we can start with an open circle. And here's a tip. I tend to like to put an open circle first, and if I decide that it's in the intersection, then I can close it. Now, why would I know straight away that I'm going to need open circles on these? Well, these circles are both sitting on dotted lines, aren't they? So they're effectively part of the parabola. And if the parabola itself isn't part of this region, then that point can't be either. So I can actually see without even checking that these both need to be open circles. But I also need to label them, and I haven't done that yet. So solving these equations simultaneously, I've already got my y equals x squared, and I've got y equals minus x plus 2. That makes it nice and easy to let these sections equal each other, and solving simultaneously, getting everything on one side, I can easily factorize this, and I can see that my intersections are going to occur when x is minus 2 or 1. Now I can sub both of those x values into either of these formulas. So let's say when x is minus 2, we square it, we get 4. And when x is 1, we square it, we get 1. So I can label this point here 1, 1. And this point over here will be minus 2, 4. And I've identified that neither of them are going to be part of the intersection. So now I'm finished. The line is part of the intersection, but the curve isn't, hence the dotted line. Now let's think how this would have changed if instead of graphing the intersection, we'd been asked to graph the union of these. Well, the union means anything that we've graphed has to be part of the union. So all of this section up here, which is above the parabola, we need to graph. And then we also need to shade everything that's actually below the line. So that means we need to shade all of this. Now, at this point, we need to think about our boundary points here. Are they actually now part of the union? Well, if we think of 1, 1, is it either this or this? It only needs to satisfy one of them to be part of the union. Well, it doesn't satisfy this one. 1 is not greater than 1, so no. But over here, 1 plus 1 is equal to 2. So if it satisfies either one of these, that's enough for it to be part of the union. So we now need to actually colour these circles in because they're sitting on this solid line here. And for unions, you only need them to be part of one thing or the other for them to be included. Now in this exercise, sometimes we just need to graph a region, and other times we need to graph, say, 2 regions and find the union or the intersection of them. This question is interesting because it looks like we're just shading a region, but in fact we're actually shading an intersection. Now the way to think this through is to remember how we solve things like, let's just take the y out of it for a moment and think about what we would do with this, or what we would do with this. Isn't it true that when we look at these, we think, hey, this 2x minus 1 must be numbers like, well, something a little less than 6, like 5, 4, 3, 2, 1, but it could actually be a negative number like negative 1, 2, 3, 4, 5. In other words, we say to ourselves, this is an in-betweener. 2x minus 1 must be between negative 6 and 6. Whereas with this one, we can identify that 2x minus 1 must take on large values, larger than 6. So things like 7, 8, 9 going all the way to infinity, but also negative 7, 8, 9 all the way to negative infinity. So we identify this as a sort of two tails situation where 2x minus 1 must be greater than 6, or 2x minus 1 must be less than minus 6. And then away we go and we solve these. These we just solve as two separate inequations with the word or in between. And this one, we can add 1 to all 3 parts and then divide all 3 parts by 2, and our answer just drops out, and it's already looking like an in-between solution. Okay, keep that in mind now while you look at this one, which has actually got a y in it, because we need to graph something here. Now, have we got this situation of an in-betweener, or a two-tailser, as I would call it? It looks like an in-betweener, doesn't it? So what we're saying here is basically that 2x plus 3y has to be smaller than 6, but it has to be larger than negative 6. So what we're saying here is this is one region, and this is another region, and we need to graph the intersection of the two. So if I write them separately, if I write this one, negative 6 is less than 2x plus 3y, and I write this one, 2x plus 3y is less than 6, we can see that effectively what we want to graph here is 2x plus 3y equals negative 6, and 2x plus 3y equals 6. Okay, let's write both of those out. 2x plus 3y equals 6 is one of our lines. Whoops, negative 6 I meant. And this one, 2x plus 3y equals 6. Let's graph those. Now, as I go to graph something like this, obviously it's easier if it's in gradient intercept form. So a little bit of work that I can do over on the side. Let's get the 3y by itself. Let's do this one first and then reason that this one will be very similar. Let's subtract 2x from both sides. And let's divide all 3 terms by 3. So we'll have minus 2/3 x plus 2. And over here for this one, this is effectively the line y equals minus 2/3 x minus 2. So both of these lines have got the exact same gradient of minus 2/3. So they're going this way, and they've got a rise of 2 and a run of 3 going across this way. But this one's got a y-intercept of 2, and this one has a y-intercept of -2. And they've got the same gradient. Let's just rough something in. Oops, silly me, I didn't think about what type of line I want. I want a dotted line, don't I? So let's put a dotted line for this one. And we'll have a dotted line for this one. Whoops, they don't look very parallel or very straight, do they? You can see what I'm trying to do there. Okay, now we could actually then label these lines. Sorry, I've made a bit of a mess. This is the line 2x plus 3y equals 6. It's the upper one. And this is 2x plus 3y equals -6. Okay, so for this one here, when we go to shade this intersection, if we've rearranged it, we could actually keep our inequality sign in there, couldn't we? And what we want is, for this one, we want low values of y that are beneath our line. In other words, we want to go below this one. But for this one over here, our x's and y's are on the large side, so we need to write them that way. And here we've subtracted 2x from each side, so the y is actually still on the large side. So we want large values of y that are above this line. So clearly shading below this line and above that one means that we've got this intersection in here. Now, whenever you use that method, or any method really, try using the other method as well, just to check your result. So let's put in a point that we know is out here and just make sure it actually doesn't make this true. Let's take a point like 0, 3. If x is 0, then we've got 0 here, plus 3 3s, that's 9. Absolute value is 9, and that is not less than 6. Great, we didn't shade out there, and that looks right. Let's take a point like 0, 0 that is in here and check that it works. 0 plus 0, absolute value of that is 0. Sure enough, it's less than 6. And let's take a point down here like, say, 0, -3, and check that it doesn't satisfy this. So we'd have 0 minus 9, absolute value of that is 9, and that is not less than 6. So sure enough, quick inspection shows us that we've shaded the right area. And sorry, this actually doesn't look all that straight. Now for our region to be complete, we've got to check our boundary areas. So as it goes along here and crosses intercepts, it would be nice to actually show that this is an open circle, so it's not actually part of the sketch because it's sitting on a dotted line. And it would also be nice to show our x-intercepts, I think, just so that it was nice and complete. So to find those, all we need to do is let y equal 0. So we've got 2x equals 6. So this was going to be over here at 3. And over here we're going to have this one at -3.